Uh, Hi everyone, good afternoon, and welcome to the second tutorial session of the day, which is about different types of fine tuning and the pre-trained LLM. So we're going to have a tutorial session, and we're going to take a look at an example of how we can pre-train by using Kift models, by using LoRa method. So we're gonna take a look at that. And as usual, if you have any questions, please just raise your hands and let me know. Okay. Yeah. So let's start with what it is. So what is fine tuning to start with? So it's just sorry, I think I had lost connection for a bit there. Can you hear me now? Am I audible? Okay, sorry for that. Yeah, so I was just saying, these models, these large language models are normally trained on a huge data set, right? Like it needs a huge data set just to get a good response from them. So if we don't have that kind of data, what we could do is fine tune. So that's basically it's in short term. It's just adapting. So already pre-trained, it's already trained model, large language model, but we want it to work for us. So like we can train it for a specific task or domain knowledge by giving it the domain knowledge by using a smaller and task specific data sets. So why is it important? So like pre-trained LLMs like BERT, GPT, Roberta, and so on are trained on a general data set, but many may underperform for specialized tasks, such as, for example, like a lot of them are trained, like a lot of them have been trained on a lot of code. That's why they are really good with code and, stories and so on and so on. But they may struggle when it comes to like some, like engineering tasks and so on and so on. So that's why they're not like they may underperform on a specialized task, even though even for programming, you can see the difference between different programming language. Since like there is a lot of data for Python, like Java, and so on and so on, it could perform better than like for the others. So fine-tuning enhances their accuracy and relevance for a specific application. So just highlight of it is just fine-tuning bridges the gap between general purpose LLMs, which we know, and task-specific performance, which could enhance their task-specific performance. So why do we fine-tune LLMs? So it could be to powerhouse the pre-trained LLMs, as we have discussed earlier. So they are trained on a vast amount of text data. So they possess very generic knowledge. So they have a general understanding of language, grammar, and vocabulary, but they might not be able to do specific tasks. So you're capable of wide range of general purpose linguistic tasks, but for our specific needs, we need to take these general purpose models and fine tune them because they are not optimized for specific or niche applications. And fine tuning adapts these models for particular tasks or domain and transforming them into specialized solutions. So how does it work? How do we fine tune a model? So the model's internal weights are adjusted based on the new data. It could be layers, and this refines this capability to enhance performance in designated tasks, which aligns the model's broad knowledge with the unique requirements of a specific application. So, of course, there's a lot of techniques to it. The easier or the most the easiest could being with prompts. We will see actually, we will also see all of them, but just keep in mind that there is a lot of ways to do it. So the key benefits of fine-tuning, increasing relevance, which overcoming lack of domain knowledge, the domain specific jargons and context, because they are trained on a huge data sets. They have generic knowledge, improve accuracy, customized interactions, tailor the model's tone, voice, and to match the brand identity. This could be done with instructions. Resource efficiency, more cost effective than training a whole model. Data privacy and security, addressing rare scenarios, which improves the performance of only unique and edge cases, and performance on a limited data. So this is really key. Some of the reasons that we actually follow this is the availability of data, the availability of resource, because it's very resource consuming, and of course we want to improve on a specific domain. So it answers these questions. So let's talk about some techniques fine tuning and other adaptation techniques. So for fine tuning, it modifies the internal parameters of the model, the pre-trained large language models, and the number of parameters remain the same as the original, but they are just modified. Distillation, which creates a smaller model, which you can call the student, and with a fewer parameter compared to the teacher, and trained on the data generated by a larger model, which is the teacher, and this is made to just efficiently deploy deployment efficiency. So it just teaches. I think there is an example. I think I can attach this paper actually, how they use this to train to actually distill. And the last one, which I think all of us are currently doing, is prompt engineering. When I say currently, when we interact with LLMs, which is just crafting specific instructions to guide the LLM. It doesn't alter any parameters of the model, but it's a train-free and cost-effective first step. Before choosing to train the model or fine-tune the model. So actually, fine-tuning and prompt engineering are complementary and can be used with each other. It doesn't mean you cannot use them together. So let's talk about full fine-tuning, and if there's a question, I think we could have a couple of minutes to it. So for full fine-tuning, I think as the name implies, it's just updating all of the model's parameters, not just some, but all of the parameters, which is weight and biases, and retain the entire model on a new and task-specific labeled dataset. So just fine-tuning the whole as a whole, so changing everything, every parameter of the model is one method. So this of course gives you the best possible performance, which of the needs instead of the art results, but and of course maximum adaptability. It understands deeply about the data, like the domain and so on. Of course, but it's very expensive, and you have a high risk of overfitting, especially for if your data set is very small, the model can use its ability to generalize. So this is very key. Overfitting and underfitting, like I think you I think because we have had classes about training. So if the model overfits on a training data set, that's really dangerous because it loses the ability to generalize, so it loses the ability to relate to other things and so on and so on. So that's one of the drawbacks, but and also static knowledge, the model becomes outdated as the data evolves, requires costly retraining because you have to retrain on that data. And hallucination, of course, could still be there. It reduces a lot, like better than the other methods, but it could still be there. Data and security constraints, it could be can be risky and sensitive to like have these data and dependent on the data quality, because if your data is not good, the performance is directly related to it. So it has a lot of a lot of advantages, but like it also has this disadvantage. So this is not what we're gonna do because we don't have nearly as much data, computational resource, and so on and so on. So here's where PEFT comes in, which is parameter efficiency, efficient fine-tuning. But before that, like, is there any questions, like anything that's not clear? Maybe if my audio was not clear at some time, and so on. So was that clear? Is everything clear? Is everything good so far? Any questions? Okay. Okay, so let's talk about like paved models, like paved method of fine-tuning. So the core idea is freezing the vast majority of pre-trained LLM parameters and just fine-tuning only the subset of the newly added parameters, which we call adapters. So we're going to take a look at what we mean by adapters, but basically the full fine-tuning method changes all of the parameters or modifies all of the parameters, but here we freeze most of the parameters, but only train or fine-tune on the small subset of the newly added parameters, which is the adapters. So why is it essential? Because it's very resource efficient. It reduces the cost of computational and storage cost, as well as low need for we don't really need nearly as much data set to train. It mitigates catastrophic forgetting. It just prevents the model's general knowledge while specializing. Preserves, and better for low data regions. So as we have said, and portability. So it's very small checkpoints, so making it deployment easier. Like you can deploy it. Even now, you're going to be deploying it on your local, so it's very lightweight. So let's talk about the methods, like some of the methods, which is let's start with the LoRa, which is low and rank adaptation. So this is just injecting small trainable low rank matrices into each layer of the transformer architecture. Only these new metrics are trained rather than the whole or the whole parameters. And so this really reduces the trainable parameters, reduces checkpoint size, no inference latency, maintains model quality and speed. So we will also see this in the example. So I think it will be like a lot clearer there, maybe. But of course there is a disadvantage. There is a gap compared to for full fine-tuning for complex taxes. So this is obvious because it's trained only on a subset of like our low rank metrics into the transformer architecture by injecting them, and can be more complex to set up and optimize, especially the optimization. I personally find it to be a bit complex because sometimes it will work with just a small change, but sometimes it would, you know, yeah, it could be a bit harder or complex. So let's talk about adapter tuning. So this is just adding small tunable adapter layers into the transformer blocks. Only these adapter layers are trained rather than the whole thing. So it's high memory efficient and requires low compute. Can achieve performance and comparable to the full fine tuning. Facilitates quick and lightweight training cycle, and of course it's very limited in capturing high complex domain knowledge, and performance scaling is very intricate task in this case. But we will see the LoRa in the demo actually. Of course, the rest are instruction prompt tuning, which you can consider as soft prompting. So it's just adjustable optimized vectors like integrated with the input text. So the model parameters remains frozen. So it's just stream free, and the core of the core model, it's very cost effective and simple to implement. Prompts are human readable, and you can interpret it easily. Of course, it's very less direct control over the model's process, learning process. Finding effective prompts can require trial and error. Prompts may not transfer well to other tasks. So, for example, I think we have an example here, guiding an LLM to generate SQL queries by providing examples. So this is called two-shots prompting. So there is a lot of methods of prompting that I believe it's better if you take a look at them, because there's a lot of ways to prompt. So this example is actually an example of few shots prompting, which is providing it with examples of what kind you need to see. Like, so I want to generate this. So here's an example of like what I need, and so that's called few shots prompting. And the last one is instruction fine-tuning. So it just trains the model with example that explicitly demonstrates how to respond to a command. So do this, if you are asked this, say no, and so on and so on. Focuses on teaching the model to follow structured command and produce constraint outputs. So it's very improves the response and consistency and predictability. It requires less data than fine-tuning, full fine-tuning, and effective for generating structured outputs. But it's, of course, it's limited capability for deep domain adaptation and shapes behavior rather than imparting new factual knowledge. So this the main reason that we use instruction fine-tuning is not to change what it knows, but to shape how the model responses. So just instruction on what to do, like how to answer, how to respond, and so on and so on. So here is just a table of comparing these 5 methods: the full fine-tuning, the LoRa, the adapter tuning, prompt tuning, and instruction fine-tuning. So you can just take a look at them when you have time, when you are going through the slides and get an understanding of it. So at the last slide, in conclusion, so full fine-tuning offers best performance, but it's very resource intensive and creates static models. But the PIFT, which is of course the LoRa, the adapters, and the prompt, provides an efficient and accessible alternative, mitigating many of the drawbacks of the full fine-tuning process or method, and are ideal for most practical applications. So, and lastly, the fifth one, which is instruction fine-tuning, is just to control the model's output performance and consistency, so it becomes more predictable. So choosing the right method depends on the amount of data you have, the computational resource you have, the performance you want, or that's required for the model, the complexity of the task at hand, and how the maintenance needs. Yeah, so that's just it for the theoretical part. Do you have any questions, guys? I think we can have some time for question and answering. Let me get this notebook here. So any questions, or is it clear? So I was planning on, providing you with a different example, but it's taking very long. I started training, I think, early in the morning, 6 in the morning, but it's still training. So let's work with what we have. Okay. Can you see, can you see my screen? Okay, before that, let me, yes, no, oh, okay. I think I got the wrong notebook. Okay. Okay. What about now? Okay. Okay. Good. So let's see. Okay. Yeah. Okay. So let's see this example. So this example is so what I did was, let me just explain the dataset first. Still no, but I think Magdas, it's for you because I think the rest can see. Maybe can you check your network? Okay. So the data sets that I choose, or that we're going to be working with, is the IBM, IM PV. The data set is just trained on let me show you an example. So here we have, you can see that's a sentiment data set. So here I have rented. So it's just for, so I don't know if you know, it's just where people review movies. I think I'm not sure if you can see movies from that site, but you can definitely review movies from that site. So it's just a site. I think you can search it and take a look at the site IBDM. But basically, it's just that the data set is labeled with, we have the text and we have the label. So the label tells us if it is a positive review or a negative review for this case. So like I printed a I'm Curious Yellow, which is I think the name of the movie for my video store because of all the controversy around it. But when it was first released in 1967, I also heard that it was the first. Okay, it was that first it was seized by the U.S. Customs if you even tried to get into the country, and so on and so on. Therefore, like blah blah blah. So. So it talks about the movie. I just wanted to see. I just wanted to show you. I think this is a negative review, so I just wanted us to see where it got that from. So detail bar, the issue, I mean, asking political and so on. Okay, what keeps me about I'm curious is that 40 years ago was considered pornographic. Really was just blah blah blah. Yeah, but we get the point. So this is the review. This film doesn't how much of the plot and so on and so on, but it finally get a 0. So we will see the 0 label means it's a negative review. So yeah, so this is a negative review. So you can go through the comment or the like the review and see why it was labeled as 0. So we have this data set. So the IVDM is just that one. So we have for the trained data set, we have 25,000 rows, and for the train, of course, for the test, of course, we have the same, and for that unsupervised, we have 550,000 rows. Yeah. So first thing that I did was I used the first thing is just to tokenize the data, the rows, the text that I have, because it has if you can see, it's very long. Plus, for it to understand, we need to have tokenized data because it's it understands number. So the first thing that I did was for the model checkpoint, I used the distinct BERT, which is just a lightweight version of BERT, and based that case. So this is going to be my tokenizer. So I just initiated it here, and here is just a simple function that's going to tokenize it. So here for the padding, you see that if the text is shorter than the maximum length, it's going to have add some padding, and it also accounts for special class and separators as well. And for the maximum length, I have gone with 528. So this is going to tokenize the data according to this. So this is going to take the text, and then it's going to tokenize it. So so I applied the tokenization function on the data set, and I renamed. So here it says label, but since the model expect this labels, so sorry, I chose to rename it to labels. So here we have label, but since it expects labels, I just renamed the column to labels. So here is just the tokenization. So it just creates the tokenizers, the tokenizer config to JSON, and the config to JSON, and it's going to tokenize it and then maps it. So after that, so for the since we already have the tokenized data set here, and then we already have, I think, oh, okay, so you can't see it here, but and we have tokenized it, and then the next was fine-tuning it. So for this session, I chose to go with the PIFT LoRa method, and here we can see that from the LoRa. So I just this just for importing the dependencies, and then for the base model, I used the model checkpoint which we already have, and the number of labels to be 2, which is for either positive or negative, 0 for negative and 1 for positive, which is the number of labels that I have. So I think for your case, I'm not sure, was it 7 or 8? Maybe you can correct me. So I just chose the number of labels, and for the model checkpoint, we already have the distant birth based on like base uncased. So which is just like a lightweight of the birth model. So for the configuration, so we have the sequence classification, the roller rank, so the dropout rate, which also prevents it from overfitting the LoRa model, and LoRa alpha is just how the LoRa updates. So I'm just reading the comments because when I was making the slides, I just wanted it to be self-explanatory. So it adjusts how the LoRa updates and blends with the existing weights, and whether to include bias parameters in the LoRa module, whether or not, and then convert the model into PIFT model using LoRa. Here you can see I used the gate PIFT model. We have the base model, which we already have here. Oh, sorry. Yeah, which we already have here. And we have the LoRa configuration, which we already have here, where we configured the LoRa, and then the trainable parameters. I just wanted to print it out here, and all the parameters. So here we just start. So here you can see the trainable parameters are 887,042. All the parameters are higher, and the trainable are 1.31%. So here, after that, let's train the loop using the trainer API. So here we have output directory. I think it's not going to be visible here, and I cannot retrain it because I think it took me. This is really like what should I say? An easy train, or like it should be very resource friendly, but surprisingly, it took me, I think, more than only the training took more than 30 minutes. I don't know why, but yeah. So what I did was I just took a smaller data set to train because of the code, like it was a big data set. So I just used 2000 for training, and for the evaluation 1000. And then, for the training arguments, so the output directory and the evaluation strategies to use epochs, I think we used the number of training epochs 2. Saving strategies also to epoch, so for every epoch is going to save. And for the logging strategy, we used steps. And for the logging step, we used 50, and the byte size per device is 8, and for evaluation as well is 8, and the number of epochs is 2, and the weight decay, which is just a hyper parameter that helps to prevent overfitting, and the learning rate is just very small actually. The step size for optimizer and push to habit first. So this is because I don't want to. I'm not working on again base and so on, and this is just arguments for the training, which I think you can use for your model as well. And for this is just for evaluation. So for the evaluation metrics, we have accuracy, and here just a simple function that's going to compute the matrix. So we have the label and the log its, and we have the evaluation predictions. So for the prediction, we use Torch. I think I have, okay, I have already used it earlier, but yeah, Torch, and it's going to give you the metric accuracy by computing its prediction and reference by referencing its limits. So this is just going to train. So the trainer, we have for the model, we have the fifth model, and for the argument, we have the trained arguments. And for the trained data set, we have the smaller version of the trained data sets. So like it's a huge data set. So even like more than 13 minutes was for the smaller one. But for the bigger one, it didn't even finish after an hour. So I just went with the smaller one. And for the evaluation, of course, I used also the 1000 evaluation. And for the tokenizer, we already have the tokenizer. And for the compute matrix, we just use the function that we have defined earlier. So let's train. So this is for training. So we just trained it here. So we have 2 epochs, and we can see the loss, the validation loss, and the accuracy. So accuracy is going up, but the loss is going down. And for the evaluation results, we can see here, I think, okay. Runtime, this for the evaluation sample per second, and so on. So the evaluation loss is 41.08, which is from the second report, and the evaluation accuracy is 82%. So this is not a good model, to be honest. It's not a good model, but since it's trained on a smaller data set, I think it's acceptable. But it's very low. So if I gave it maybe 2 more reports, it could go up to 85 or like maybe even 90, but rarely percent accuracy. But yeah. So this is just so I just gave it a couple of examples. Here we have, I absolutely love this movie. The acting was great, and the story kept me on the edge of my seat, which is a positive review, and the plot was dull, and I nearly fell asleep. Would not recommend, which is a negative review. So I just wanted to see if the model is good with this test. But you can, of course, we can have a larger data set, and in order to see how good it is, and even download the model and like deploy it and let others test it as well. So here, if you can see, it have successfully, I would say, predicted the positive and the negative reviews successfully. It just says positive and negative because from the function, the predict sentiment function, we have set it to say positive if the label is 1 and negative if else. But since it only has 2 labels, so it's going to say negative if it is 0. So yeah, so that's it for just explaining or just to introduce you to PIFT and LoRa. I hope it's clear. Let me check. Oh, okay. So, okay, yeah, I think. For the Amharic, I was trying to use, it's just at, you're not going to believe, but it's just at 3% after 2 hours. So that's why maybe I would just use like a smaller capacity, do it with that and share it with you guys. But I think for now, for just introduction sake, I think this is enough. I hope it's clear. How do you feel, guys? Is it clear? Do you have at least a grasp about what needs to be done and how to do it? How to get started with it? Okay. We have two. What about the rest? Is it clear? Okay. Okay, good. So is there any clear question? Yes, I will share the slides. And what do you mean? What about the Amharic version Abdulaziz? Or are you talking about the example? But like, if you are talking about how to train Amharic, like Amharic dataset, it doesn't change. It's not different. If the model is already like Amharic friendly, or like if it is trained on Amharic dataset and it's not Amharic, it doesn't change. The process does not change. The process is the same. I just used a different dataset, but it doesn't change. But if you are talking about the example, yeah, if it finishes in time, of course, we'll share it. Maybe if you are curious, I was using maybe share the. Yes, is that a question? Yes.
Okay.
Yes.
I think on the pre-trained model, sometimes from maybe on the different purpose, maybe for research or other thing, they asked us doing in the custom model instead of the pre-trained. So what is the functionality of doing custom model over on the pre-trained model? This is my first question. And the second one, on the dataset classification, as we see earlier, you divided for training and test data, like 2000 to 1000, like things. And also in real world, the data is classified for training and test, like 80 to 20 or 70 to 30 something. But also there is validation. So for that validation, are we use dataset like testing and training, or what does it mean by validation means? And the third one, what does it mean torch? Is that like a framework for like the TensorFlow or?
For training, yes, yes.
Okay.
For the last one, yes, yeah. It's just, I think one is made by Microsoft and the other is made by Facebook, I think.
Okay.
But I will check and yeah, but yeah, it's similar. And so it depends on the dataset. So for this type of dataset that I used, they came with their own validation, their own test data, and their own trained data. So you can use them as they are. So, but if like I think if you remember from our last session, last week's session, the dataset did not have this kind of like a classification. So yes.
Sorry.
You can. Yeah. Oh, is there a mistake? Okay.
Yeah.
So if it is not provided, like if it is not provided independently, of course you have to have some percent as training data set and others for testing. This is just to see how good your model is performing for the evaluation. So for me, the evaluation data set was the testing one. So after you train it, you test it on the data set and see, since you already have, okay, so let me explain it like this. So for your training data set, you have the question and the answer. So the student is going to learn both the question and the answer. And for the test, you have the answer and you give the question to the train. or to the student. So the student is going to answer, and you're going to cross check, like the answer from the student and the answer you have to see how good the student is. So maybe if that example is better, you could also like consider
So
that.
it means validation means checking the performance of
It's
the training.
validation. Yeah,
Okay.
of course. It's just
Yeah.
to validate. You can
Okay.
say that I was actually talking about the test, but yeah.
Okay. Okay.
Okay.
And
Thank you.
uh,
Okay.
trend
The
the
first one,
custom.
it wasn't clear. So, okay.
For example, as a researcher, actually there is a pre-trained model like, for example, uh, ResNet or VGG or other type of pre-trained
Mm.
model. Yeah. But sometimes for research purpose, the advisor ask us like using custom model instead of pre-trained. They want to do custom models instead of pre-trained. So is that much necessary uh, doing custom model? I think.
So, for custom, are you saying fine-tuned model? I think I'm not
Yeah, taking
getting
or
it.
inheriting the model, maybe for example for image classification, there is CNN, yeah.
Oh,
But
okay. So for fine-tuned, okay, for
yeah,
special cases.
maybe
Yeah,
I'm
of
changing
course.
layers or something. Yeah.
Yeah, yeah, of course. So, of course, it's necessary, uh, but it depends on the kids. So, for instance, like maybe if you don't mind me asking, um, okay, what do you do like for like, like what do you do with a model? So, okay, so like I think it's better to give example on my own, on
Okay.
myself. So, if I want
Mm.
a model or to have an LLM to help me design mechanical components,
Mhm.
the current ones that are already available, you can even take a look at huge models like ChatGPT and so on and so on,
Yeah.
like the OpenAI models and so on. So even they are not good for for this type of purposes since I have tested them. So like having this custom model that's trained on like the designs principles, the principles of designs with examples and so on as a uh, or previously designed works and so on could help me better do the job, like could help uh, the model do its job better if you get me. So having a custom model is not a must for everything, but it's better for your case. Like I don't know, like the question is very generic, and I don't know how. But
Yeah.
of course, yeah, it depends on the case.
Okay,
If
depends.
your case is for it's very specific and very nuanced, like if it is very domain, if it needs very like domain knowledge,
Mhm.
since the models are trained on a lot of text data, they have general
Mm.
knowledge rather than domain knowledge. So if I ask for example, like I don't know, I think they have fixed it, but if you ask about a certain word, I'm really sorry. I think I have forgotten the term, but if you ask it about a certain thing, it's going to answer from a different perspective. So some words have a different meaning for like medical case and a different meaning for other cases. So
Yeah.
they are very generic. They may have like under difficulty understanding you what you want to do and what you are referring to.
Okay. Okay. Thank you.
Yeah. Yes, Burma.
Okay. My question is for many African language, like for just a complex grammar. So can we use with Masca project or Mascan project? Can we handle the problem with the Mascan project? How to create the good
No.
organization?
Like so it's a good start, but it's not as good as like I hope it would be, but it's a good strategy. But for the tokenization, I think with the data you have, I think you can use, like, I think we have referred a couple of more models for this one. If you have checked on the challenger document, Girma,
Yeah.
I think you can check that as well, but yeah, they're not as good as I hope they would be. But of course, it's a work on progress. So is that clear, Girma? Or
Yeah.
you have muted? Okay, I will keep it down as a yes. Okay, I think there are some comments. Share me the libraries, please. Okay, libraries. Okay, I will share like both the notebook and the slides. I think I can even share the slides right now. But I will share it on the drive as well, so be on the lookout. Okay, I think the users in China are referring to the question with Gabriel, but thank you for sharing, guys. Yeah. So, Girma, I think for your question, like for the model I was building, I think it was a year ago. I had to build my own tokenizer, but maybe on Hugging Face you will find it. I will share it with you, so that you will try it and see if it is any good. I think Girma work. Okay, maybe it's not here, but yeah, it's not good, but yeah. Okay, I think, is there any question, guys? Questions. Okay. I think you can find it on Hugging. I think Hugging Face, I think I have uploaded it, and we actually used that tokenizer for building our model when we were, like trying to build it. I think it's not similar to this. Yeah. Okay. I think I have used a lot of time. So is there any question? Is everything clear, guys? Okay. I hope it is. If it's not, please just reach out to me on Slack, and we will have a discussion on it. All right, guys. Have a great day. Thank you for joining and participating.